Hello and welcome to the lecture Generative Modeling. In this lecture, we first introduce generative learning models. Then we try to understand what are the statistical understanding for generative learning models. Then two important concepts, maximum likelihood and density estimation we discussed. And then we study about different generative models. Today, we'll start generative modeling. Now, as of now, whatever we have discussed, they are mainly discriminative learning or the models which follow the discriminative modeling. What is the main way of doing discriminative modeling is that if we consider a vision task like image classification, we try to learn by discriminating some images. What is the example? If there is a cat image and we want to know that given a image is cat or non-cat, then we try to understand what factor or what attributes discriminate between cat category or cat class and non-cat class. So when we are given a set of labeled or annotated examples, we try to find out this mapping function. That function is essentially a discriminating function, and that discriminating function is going to say that given a image is a cat image or a non-cat image, and likewise. So the discriminative learning basically follows a procedure. We are trying to find a hypothesis function or a mapping function from a class of or a set of annotated example to a set of labels, so that by virtue of discriminating attributes, when a new instance is coming, that we can say this is which class it belongs to. So in general, we do not try to understand what are the intrinsic or what is the statistical distribution of the given samples. Now we are going to a different paradigm of learning called generative modeling. Now in this approach, it mainly aims to learn the underlying probability distribution of a given data set. Now that is the first fundamental difference between discriminative learning and generative learning or modeling, that here we not only happy to find out the mapping function, rather we aim to learn the underlying probability distribution of our sample or annotated samples or a given data set, whatever we say. And what is the purpose? After understanding the distribution, our goal is subsequently generate new samples. These new samples, what we are generating, that are statistically consistent with the observed data. Observed data means given data set. That is the major agenda of generative modeling. Now you can see here in this image, this is a generator. So this is a neural net. Okay. From a random noise. So random noise is a latent space kind of. Now this random noise, let's say at a z, p of z means the z space, that using this generator, we generated a data distribution is called d bar for say. Now g of z, z is basically a random noise and g is a generator, so we can get this data distribution. Right? Now what is the intention is that given a data set, this distribution, what we want that these two distributions should be very close. So we measure a statistical loss or statistical distance between d and d bar distribution, and we want to minimize this loss. So we have a kind of this loss is back propagated to this generative model so that it changes its parameter such a way it more similar sample can be generated. So now this is the setup. Now how it is consistent with this statement? Now if you think a bit in different way, that this is a observed data or a given data set, real data distribution, what actually we try to understand, actually without knowing the data distribution, we try to model this distribution in way how we are going to try to understand. We are generating some samples, and when generating these two statistics, these two data samples should be statistically closed. So what does this mean? We in a other way around, we are trying to find this statistical or unknown statistical distribution by virtue of generating the similar samples. Once it is been trained, this generative model or this generator, without knowing the actual, we don't know this is a Gaussian, mixture of Gaussian or what distribution, the unknown distribution known by given the samples, and but we model it that with learn the underlying probability distribution. This probability distribution is being learned of an unknown distribution so that it can generate the similar samples. So this is the basic idea of generative model. Okay, so let the training samples be drawn from an unknown data distribution D. Now this is the unknown data distribution D. A generative model learns a parameterized approximation. Now, why parameterized approximation? Now, this is a parametric model, this generator, that is basically of g of theta, you can see. And what we want to do? We update this theta so that we can find the generator which generate more accurate samples or more similar samples real data distribution. So parameterized approximation given to this distribution by mapping samples from a simple latent distribution like this, typically random noise Z, to a data space neural. So this is the basic idea of generative modeling. Now we try to understand how this kind of model is being trained. Now, what is our basic objective? As we have mentioned, that basic objective is that this generator is a neural network, or better to say a parameterized model, neural model, and that take the input from a random noise, the latent space, and generate some outputs. And these outputs, the distribution of this output is such that it mimic or it's very similar to a given distribution, or it's a real data distribution. So what is the basic understanding here? That first we generate, when we start generating or start training, we use some random values as the weights or parameters that will generate some samples. It is generated samples. Then we try to find out what is the difference between this distribution and this real distribution, generated distribution and real. Definitely there is the loss is bit high, and accordingly this loss we try to update the weights, and these things are basically going on. So here what we say, model parameters are optimized, are being learned to minimize a suitable divergence or statistical distance between real data distribution D and the generated data distribution D bar. That is exactly okay. So now, depending the model's framework, this discrepancy or this difference may be quantified using different kind of statistical L1, L2 norm, Lever-Kullback divergence, Jensen-Shannon divergence, other distributional distance measures. So different loss function we can use. Basically, loss function is the statistical distance between two distributions. Now, what happened when the training progresses? That this generator learn how to generate the samples which are very closer to this underlying distribution or real data distribution. Now there is a one question. What is our objective? Is it objective that we are going to generate the same samples? No. That is very important. These samples are being generated which follow that given distribution, or these two distribution D and D bar is very close. That is our objective. But the samples what we are generated, it not present in the real data distribution, and that's why it's a generative. They are generating new kind of samples which follow a given distribution. Okay, so that is also important. When training progresses, generator learns complex structure and statistical characteristics of the underlying data distribution, so that we can get the more and more close features or close samples as the real one, but not the same sample. That is very important. Now here we said that once adequately trained, the model can transform previously unseen random noise vector into a novel synthetic sample that closely approximates. Now say novel, it's a new samples, close, but these samples is closely approximate the characteristics of the original dataset. It's true dataset, real dataset, while remaining distinct from the observed. It's not the same, but it follows the same distribution. That is the main concept of generative modeling. So thus, generative modeling provides a powerful framework for learning complex data distribution and generating realistic, diverse and statistically representative synthetic data. So that is very important to understand. These data what being generated are not present, but it's a very similar kind of data. That is very important to understand. Now we try to understand a bit statistically how generative model works. Now, generative models statistically characterize the underlying data generating process by learning the joint probability distribution of the observed feature X and their corresponding class level Y. Now here, please try to understand there is a two different things. One is feature vector and their corresponding class levels. Now if we assume the feature vectors X and the corresponding class level Y, then from that point of view, we say there is a X and Y, two things. So it's a joint variable X and Y. So the joint probability distribution of the observed feature X and the corresponding class level Y. So that is very important. So it's a joint probability distribution. Now let the training observation independently from the unknown true distribution. This unknown true distribution is basically this P data of XY. Now this P data of XY is unknown. We don't know the nature of the distribution, but what we know that this distribution by a means of some given samples and the corresponding class levels. Okay. So where X represents the observed feature vector and Y represents the associated class. So this is the our true distribution, a real distribution. Okay. Now, since the true data generating distribution is unknown, that one thing is very confusing here. Somebody that it is a known distribution. It is known by virtue of its samples. Okay, so it's an unknown distribution. A generative learning algorithm estimate a parameterized distribution p theta xy. Now, what is we trying to find? That this joint distribution we trying to estimate or approximate. And when we are trying to estimate, we use a parameterized distribution p theta xy, where theta denotes the model parameters, such that p theta xy is very close to the p of theta xy. So what is our basic try to understand? We try to know this, we end up with this p theta xy, which is very close. That means we know this p theta xy. Okay. Now this joint distribution, this is also a joint distribution that we have known. It is a parametric joint distribution or parameterized distribution. The joint distribution can be factorized. It varies from the multiplication rule of the statistics, that this p theta xy is equal to p theta y into p theta x given y, where this p theta y represent the class prior probability. Y means what? It is the prior probability of the classes. Okay. So class prior probability indicating the probability of observing a particular class, that how this particular class is probable. Okay. So this is, I repeat, this p of theta y, this is the class prior probability that indicates the probability of observing a particular class. Now there is a cat class. So what is the probability that cat class being observed. That is the prior probability, because we don't know that anything else at this moment. And then p theta x given y. So what is it's represent the class conditional probability density. What do you mean by class conditional probability density? That it describing a distribution of feature vectors within that class, and that is very important. Now, given this class y, what the distribution of feature vectors of this class within that class. So it's class conditional probability density. Actually, density function means what? Probability density given the distribution, given the class. For that particular class, what is the probability density? So it's called class conditional probability density. Now, during training, the model estimate these distributions, this p theta y and p theta x given y, from the available observation, this p theta x because this, and adjusts its parameter to obtain the best statistical representation of the underlying population. That exactly we want to do. So what is because basically doing our training? The model try to estimate this distribution p theta y and p theta x, x given y from the available observation is p theta xy, and adjusts its parameters theta such that to obtain the best statistical representation of the underlying population. So we have to find this theta such a way that this particular the best statistical representation of the population. So in likelihood based generative learning, this is commonly achieved by maximizing the joint output of the training data. Now, the basic idea was what? That we find that we try to basically try to optimize this p theta x1 y1 that we have seen here, that this is p theta xy. Now, the basically what this joint probability distribution is this, where we can factorize in this way p theta y into p theta x given y, where p theta is equal to the class prior probability and px given y is the probability of observing a particular class. Okay, that's called class conditional probability density. Now, the idea here is basic. In likelihood based generative learning, that what we try to find out such theta that is going to maximize only this thing, that we put a summation and put a log here so that we can get a summation is much easier to do. So that's why we put 1 to n is n number of samples p of theta xi y. Now, if we can factorize it, it can factorize in what we have seen here, that p of theta x comma y, p theta y, p theta x given y. So in this way, so this is to factorize class prior probability and class conditional probability density. So we can just write it here. So this factorized from the objective can be expressed as this. Thus, the model learns both how frequently each class occurs. That means this is the class prior probability, and how the feature values are statistically distributed. That is given a class yn, how these features are statistically distributed. That also. Once this distribution has been learned, they can be used for the generation and classification. So that is the most important. To distribution we learn by virtue of this likelihood based generative learning or generative learning. Now, Here, for a given class Y, new feature vector can be generated by first sampling a class according to the p theta y. Now, given a class Y, you have to first do sampling a class according to p theta y, because this is a class prior probability, and then sampling a feature vector from this corresponding conditional distribution. But given this Y, because we know p theta y, what is the feature distributions? Now, conversely, we can get that different, that for an observed vector x, the learned distribution can be used to determine the most probable class to the base. Now, this is we have to, given a class, we have to generate the conditional distribution. This basically sampling the feature vector from the corresponding conditional distribution. So, we given a class, we get this feature vector, generate this feature. So, this is a typical generative process. Now, conversely, for the observed vector x, so if we can observe a vector x, so given x, what is the determine the most probable class? So, we can find the one. So, it is basically kind of classification terms. So, we can easily do that p of theta x y, this is probability, to p of theta y, that is it, and this is the samples of given samples. This can say what the sample space we are being given. So, evidence. Therefore, from a statistical perspective, generative learning estimates the joint probability distribution P of xy decomposed into class priors and class conditional densities and use the learned probability structure to generate new observation and infer classification. This provides a unified probabilistic framework in which the variability and relationship present in the training data are captured rather than merely learning a direct mapping from x to y. So, this is the how it is different from the our discriminated method. So, it is a unified probabilistic framework in which the variability and relationship present in the training data are captured rather than merely learning from direct. So, this is the basic. Now, we are going to understand another very important concept called maximum likelihood estimation, which is a fundamental statistical method used to estimate the parameters of generative model. The central idea is to determine the model parameters that make the observed training data as probable as possible under the assumed probability distribution. Now, there is some observed data. Let's say this is the observed data, that dxi yi is I to n. But this is our kind of. So now, if we have to understand this data distribution, then to understand this data distribution, Emily answered the following question. So, what parameters makes the observed data most probable under my model? So, what we are going to find, we are definitely going to find a probabilistic model or parametric model that is best represent this data, this observed training data. Now, suppose this observed training data consists of n independent samples. So, this is the xy, the feature vector, and the corresponding level. I use for capital N. But the samples are assumed to be drawn from an unknown true distribution, that is p data x comma y. So, this distribution is known by virtue of the samples, but actually it is an unknown distribution. That is the real distribution. Okay. Now, a generative model defines the parameterized distribution P theta. We cannot find that this model distribution is unknown, so we try to approximate, where theta denotes the model parameters. The objective of the MLE is to find the parameter value theta star that maximize the probability of observing the available training data. So what we're trying to do? We're trying to do that this p theta xy is basically represent the underlying distribution. So that ML is to find the parameter value theta star that maximize the probability of the observing the available training data. Yet some model this is a kind of with parameter theta based statistical model that best describes this data points. So that is the experiment. So theta star is argmax is equal to 1 to n, and this is basically a joint probability. So we can multiply. This product of probabilities is referred to as likelihood function. That is equal to 1 to n p theta xi comma yi, that given the distribution d and parameters theta. That is the likelihood of theta. Okay. So this is the likelihood function. Now, since multiplying a large number of probabilities can be computationally inconvenient, we put a logarithm and make it a summation. So logarithm of the likelihood is generally maximized instead. This gives the log likelihood object. So what is the log likelihood? It's basically same thing, a similar thing, that this same thing is basically given here. Theta star is argmax theta, that we put log so that we can this multiplication replaced by the summation equal to 1 to n log p theta. So for a generative classifier, the joint distribution can be factorized as p theta x comma y, that what we have seen before also, p theta y, p theta x comma y. That this is the class probability, class prior probability, that probability of each class, and it is what the distribution of the feature within each class condition probability densities. So therefore MLA objective becomes this theta star argmax theta 1 to n. We can put this as this p theta yi plus log p theta etc. This means that the model learns two important statistical components: the probability of each class, that is p theta y, and the distribution of the feature with each class p theta x given y. Okay. The resulting model attempts to assign high probability to the samples that are representative to the observed data distribution. That is very important to understand. The resulting model attempts to assign high probability to samples that are representative to the observed data distribution, and low probability to the observation that are statistically inconsistent. So those samples which are from the distribution given a high probability, and those samples which are not supposed to be of this distribution, that is inconsistent. So MLE can therefore be understood by finding the probability distribution that best explains the observed data. Finding the probability, so that is actually we want to go in the objective. We try to find out a probability distribution given the observed data. So this MLE can be used for this. With sufficient and representative training data, maximizing likelihood encourages the learned distribution. That's why to approximate the underlying data distribution, we do x comma y. So this learned distribution is approximate to underlying data distribution. Now, why it is called this process called? Because we know once p theta xy is learned, we can generate levels. This is that we know how to do a class layer probability and generate the data at p theta x comma y. That is called the conditional. This thing is basically uh, thing that class priors and class conditional densities. These two things, this and this. Okay. So here we can say that these two things we know, so that we generate unconditional samples with theta x from this. Thus, the model describes the data generating process and thus generating. Now, based on the way generative model works, there is a three main types of generative models, namely explicit density models. These are true density estimators. They really estimate the probability density of the observed samples. The particular models that used as or termed as explicit density model are autoregressive models, normalizing flows, variational autoencoders, etc. Another very important kind of density models is called implicit density models. These models do not compute the Px explicitly. The example is generative adversarial. It's also very popular generative model. Another kind is score-based or diffusion models. This is an implicit density estimation via score estimation. This is also implicit density estimation, but it uses the score estimation that denoising diffusion probabilistic model, DDPM, the score matching models. So these are the main models, generative models that we are going to discuss. So there is a from this figure copied in from Ian Goodfellow from the paper, that what are the different types of, as we have seen, the generative model is explicit density model and implicit density model. And in explicit density model, again we can say the tractable density. We'll see later what this means, tractable. It's called fully visible belief nets, made, this pixel RNN, change in variables models, non-linearity. So these are tractable density. Another thing, that approximate density. For example, Markov chain, the Boltzmann machine, or it's a variation of, so the variation of an that we approximate the density. In the case of implicit density model, there is one is direct implicit model, that is the generative adversarial network. Okay. And another is Markov chain based, that is GSM. So this will give you an idea that this kind of different type of generative model exists based on the estimation. So now we have to understand what do we mean by density estimation, and then try to understand how these models are basically, what is the foundational workflow of these models. Okay. So density estimation in generative modeling, and it's another very important understanding. Density estimation is a fundamental approach in generative modeling that aims to learn the underlying probability of a given data set. So that is the major theme in generative. Learn the underlying the problem when the data set is given. Let the observed data sample be represented. It's X data X. But this is unknown. It is just known by virtue of the samples. So what is the objective of density estimation? The objective of the density estimation is to learn the parameterized probability density, P theta X, that provides a close approximation to the unknown data distribution. That means P theta X is very close to P. Now, here we have to understand, already we have come across this stuff. Here again we repeat. What is theta here? Theta is the parameter. Now, we don't have the exactly this distribution because it's unknown. Now, we try to approximate this distribution by virtue of setting these thetas. Okay, theta is a parameter, so it's a parametric model. So that this statistical model or this probabilistic model is very close to this observed model or observed data. So what we basically say, the model parameter theta are optimized by maximize the likelihood. That we know before also. Yeah, how actually this theta is of the observed training samples, or equivalent by minimizing the negative buffer. So L of theta. So this is the likelihood of theta. Is basically 1 minus b in I is equal to n and log of p theta x. Pi is the number of training samples. P theta x again is the property assigned to the model. So that is the basic understanding. Okay, that we try to minimize the negative log likelihood. Negative. Okay. Now, once the probability density has been learned, the model can be used not only to estimate the likelihood of the new observation, but also, depending on the generative architecture, to generate new samples that follow the learned distribution. And that's why it's a generative. I repeat this. Once the probability density has been learned, so this probability density we can understand that, okay, we can model it like it, and it's very close to this. A model can be used not only to estimate the likelihood of the new observation. So we estimate the new observation, but also depending on the generative architecture, generate new samples that follow the learned distribution. So it is not only estimate likelihood of new observation in the class, belongingness or kind of. Not only it will give you this thing, it also can generate new samples that follow the learned distribution. And that's why it's a generative that can create a new samples that follow observed distribution. Density estimation is particularly useful when underlying data exhibit complex, multimodal or nonlinear characteristics that cannot be adequately represented by simple parametric distributions, because it's a very complex distribution. So what are the models? Gaussian mixture model, variational autoencoder, normalizing flows, autoregressive models employ different strategies for estimating or representing distribution. So these are models. Some of them we'll discuss in detail. Now, try to understand what do you mean by explicit densities. Generative models that use density estimation in two fundamentally different ways, explicit or implicit. that we have seen before. The distinction is whether the model directly represents the evaluated probability density, or we basically evaluates this probability density Px or not. So in case of explicit density estimation, the model directly defines the probability distribution P theta x for the observed data. The training process attempts to make this learned distribution close to the true unknown data distribution. P data is given distribution. It is known by virtue of this data sample. It is unknown distribution, and we try to model explicitly this distribution. So as we also understand that this is the way maximum likelihood distribution we can use at theta argmax of theta is equal to 1.2 theta exact. Here the model explicitly estimates the likelihood or probability density of each training samples. So this is the case of explicit density estimation. So in our explicit density model, we directly specify and learn the probability density function P theta x and can evaluate the likelihood P theta x exactly or approximately. So in this case of this P theta x we specify and learn probability density function directly and evaluate the likelihood P theta x exactly. So these models perform the estimation of optimizing this argmax of P theta x or argmax theta x, which is a log likelihood. What is the major aspect? It defines a tractable probability density function. Allows the likelihood computation, usually trained on maximum likelihood or bound out. So these are the basic features of explicit density models. There is two main categories here. One is tractable, exact likelihood models. That means these autoregressive models factorize density using the chain rule at P of xi given xi, that is before the I to 120. Each conditional is modeled by a neural network. Example pixel array and pixels. This is called tractable or likelihood models. It's autoregressive. Another is latent variable models, the approximate likelihood. That example, the variation that we will see later. Why calls it the approximate? Now, there is some more these explicit density estimation models. Gaussian mixture models explicitly model the data as a mixture of probability distribution. So it's explicit. Autoregressive model we have seen is structurize the joint probability index. Another important normalizing force that explicitly calculate the probability density using invertible transformation and the change of variable formula. And VA already said defined explicit probability distribution for the latent and data variables. Although the true data likelihood is generally optimized rational lower bound rather than the computed directly. So this is the VA concept. Thus, the explicit model density estimation is central part of the model formulation and training objective. So this is called the explicit model or explicit density estimation. In other category, the implicit density estimation. In implicit generative models, the model doesn't explicitly estimate or calculate the probability of Px. Instead, it learns a mechanism for generating samples that follow the underlying data distribution. Okay. For example, a generator that transforms the random noise Z will belong to into a synthetic sample x bar of G of C. This is theta. This is a generator kind of thing. What is B it is doing? It generates samples, that is x bar, from a latent space. This latent space, for example, is a random noise. So there is a generator kind of thing, parameterized with theta. Now, this generator is trained so that the distribution of generated sample P of generated X is becomes similar to the real data distribution P. Okay, so this is very interesting that we are not estimating at Px. Rather, we use a neural net or a parametric model that generate the samples, is a synthesized samples, generated samples from the noise as X bar. And we try to learn this generator such a way that the distribution of generated samples at P of G becomes similar or very close to the real data distribution. But however, the model doesn't provide this necessarily provide an analytical expression for Pg of X. The most important or most popular example here, genetic adversarial network, is a classical example of this. What this generator do there? Generator learns to produce samples that are indistinguishable from that. We'll see when we come to GAN. There is a two neural network are trained in parallel, one at a time, but it is working as a. And in the GAN, the generator is try to generate samples that are very close to the real data distribution. And discriminator, what is the rules of discriminator? That try to differentiate between generated samples and the real samples. So this neural network is somewhat competitive with each other. The generator is trying to generate samples that discriminator cannot discriminate. This is generated or real. On the other hand, the discriminator is learned such that it can differentiate between real samples. So here the generator learns to produce sample indistinguishable real sample, while discriminator provides feedback the difference between real and generated. Therefore, GANs learn the data distribution implicitly through sample generation rather than explicitly estimating the probability. And that's why it's an implicit distribution approach. Okay. Now this is implicit density models, that these do not compute Px explicitly, rather they run a sampling procedure or match distribution. That would say that defines this GAN is this, where x is equal to z, where z is equal to. But they never compute Px. So they are generative models because we just put it in the more compact form. Now another kind of models is code-based or diffusion. Most important examples is denoising diffusion probabilistic models. Nowadays is very popular. Another is score matching model. We estimate the score function, as this is basically the delta x log of px. It's basically the kind of gradient. They don't estimate density directly, but they estimate its gradient. Okay. So they perform the implicit density estimation via score. We'll see. So in this class, what we have discussed, we first introduce the basic idea of genetic models. Then we put some statistical understanding of how genetic model works. Then we try to understand maximum likelihood density estimation, statistical procedure, and we'll see different genetic models. In the next lecture, we'll start autoregressive genetic models. Thank you very much.